Can you hear me in the back? Yes. What about you standing up? Can you hear me? Yes. Excellent. Thank you. And thanks to the organizers for the introduction and for setting me up in this nice hotel not so far from the Opera House. I talked to a guy in the hotel and he said that some of the best hours of his life he owes to the opera. And so I said, so you often go to the opera, don't you? And he said, no, but my wife does. Do we have anybody in the audience who understands German? Do we have anybody in the audience who does not understand German? Do we have a third group which doesn't even understand the question? So I hope this is not one of these situations where everything is done in English and neither the audience nor the speaker knows much about English. Let me tell you about my attempts to build a general problem solver, which is always following the same basic pattern. You have a general purpose computer, such as a standard computer, a Turing machine, or a recurrent neural network, and on these computers you can run arbitrary programs with loops and recursion, and you want to solve a problem, so you have to search this space of possible programs until you find the solution. And this has been the defining question of everything that I have been doing for almost 40 years now. And the real, the most challenging aspect of that is to do it in a general way, such that you don't have only a learning machine that learns programs, but also learns to improve the learning algorithm itself without any limits. This is my name. This is how to pronounce my name. And I was born in the 60s when there was a guy called Good who talked about superintelligence and about self-improvement. And the idea was, if you have a really smart machine that knows how to improve itself, then it becomes even smarter, and it is even better at improving itself, and so on, without limit. And what I then tried to do is to implement that idea. And the first thing I tried was in 1987 at this university. So in 1987 I published my diploma thesis, and this is the cover of my diploma thesis, which is about meta-learning, where you not only learn some domain-specific behavior, but also learn the program that does the learning itself, the meta-learning thing, and also the meta-learning algorithm without any end in the hierarchy, such that you really have a general purpose thing which, no matter what is the domain, learns to adjust its learning algorithm such that it solves the problem. And the first thing I tried back then in 1985 at Siemens, where they gave me a symbolics list machine, 1,000,000 times slower than any computer today. And there I implemented something which is now known as genetic programming, which goes back to Kramer, 1985. And the new thing was that there was not only this evolution of programs that try to solve the problem, and the best programs, they can exchange genetic material such that they become even better programs and so on. No, on top of that, there was another meta level where the domain was improving the learning algorithm itself, having a set of universal primitives such that you can write arbitrary programs, which are learning algorithms essentially that figure out how to combine these programs from lower levels in some computable fashion to get better results more quickly. And then on top of that, recursively opening a meta level and a meta level, but the whole thing terminating down there in the domain level, where you where you really try to solve a given problem. And then in 1997 I tried another thing, which is reinforcement learning, where you really have an arbitrary reward function, and any problem, any computable problem can be phrased in the reinforcement learning framework, where you try to maximize the future sum of reward signals until the end of your life. That's what all of you are doing, and what our little machines are trying to do as well. And so here we see a system which has two agents, and this is after learning. So here's one agent, here's another agent, and after learning what they can do is that this one moves over here and waits in front of this door here, while the other guy has learned to go down here and grab a key. This is the only key that you can use to go up here and open this door. Now the other guy can grab the other key in this room and move over here and open this door here. And only then, when the two doors are open, then one of these guys can go to the goal, which is here, and then there will be a reward. Which means that almost never there will be a reward. And to give you an idea how long it takes before learning to randomly achieve a goal, it takes about 300,000 time steps, which gives you an idea what kind of initial bias was there among the universal instructions in the universal programming language that was used to compute this behavior. So what was happening there? You had, again, a general purpose computer, and you had an instruction pointer, this one here, which pointed at a given time at one of these probability distributions. So there are probability distributions on actions, because what I'm listing here is action 1, action 2, action 3, and so on. For example, one of these actions is called move agent, and another one is called add. So now at a given point, this instruction pointer points to a probability distribution on the different instructions of a universal programming language. And then, in the beginning, before learning, all these probabilities are equal. Maximum entropy distributions. But there's a way of changing them, and it's completely done by the system itself. Now, what's happening now is that you look at a given point in time at these, at the current probability distribution, select according to the probabilities one of these actions. So, for example, in that case, the most likely action is move agent. Move agent is an agent moving action which takes two parameters. One is the direction, the other one is the step size. So we take the next two probability distributions to compute these parameters. Then we execute the action, and the environment changes because we move the agent, and you get new perceptions from the environment in something which is called the internal storage. So there's an internal storage which can be written or read by the system by instructions which are here among the list of possible instructions. And then it can also do internal computations. For example, it can add contents of one cell to the contents of another cell, or multiply, or do all these computable things that it can do. And then the instruction pointer goes to the next thing, or maybe there's a conditional jump and it moves to some other probability distribution, and in that way you get some probabilistic program thing behavior. Now, the only way to change these probability distributions is by executing instructions which are specialized on changing probability distributions. For example, there is one which is called inc probability, and it takes as an input as a parameter, the address of one of these probability distributions and changes, say, the fifth component from 0.1 to 0.9, such that it becomes very likely, although it was unlikely before. Then it changes its own behavior, obviously, and the program that runs these changes, obviously, by executing these changes, influences the future probabilistic program-like behavior. So you have a really self-referential system, and now the question is, how can we make sure that this system, which can modify itself, learns useful stuff? And that's when you now expose it to an environment, and in this environment you want to achieve goals, like, for example, go to the charging station whenever the battery is low without bumping into obstacles and stuff like that. And there's only one way of undoing self changes. And that's the only external force that we have in this system, which essentially is again embodied by another instruction, which is called call the success story algorithm, invoke success story algorithm. And that instruction, what does it do? It looks at the last invocation of a success story algorithm primitive, which happened maybe at time step 5 billion. And then at time step 5 billion 200,000 steps later, there's another instruction like that, invoke success story algorithm. Now it looks at every self-modification that the system itself executed during these last 200,000 time steps, and it just measures, did I get more reward per time in that most recent interval than in the interval marked by the previous checkpoint? If not, then I undo all those self changes such that the most recent checkpoint is the previous one. If it's now better than the one before, if I'm now getting more reward per time than during the interval before, then I leave it as it is. Otherwise, I keep popping off self-modifications. So at a given point in time, you have to have a mechanism which keeps track of previous self-modifications such that you can undo them. And in these applications, then you really have a stack of self-modification memories, if you will. And then it turns out, as you are trying to solve a complex problem like this one, only the top 10 self-modification sequences are still kind of unstable, and everything down there in the stack below is very stable and doesn't change anymore. Which means that each self-modification sequence that is still there, that still exists, was followed by more reward per time than all the previous ones. So you have a history of reinforcement accelerations by definition. Well, that's a proof. And then that's what happens in this case, where the two guys, the two agents that collaborate and compete in a certain sense, where they learn to go down from 300,000 steps per trial until solution to about 5,000. So this is after learning. Well, then I try to figure out what is an optimal way of building a universal AI, one that is not only empirically motivated, like the success story algorithm thing, which I just mentioned, but where you can show that this is the best possible way of improving yourself. And the result is the Gödel machine. Gödel, 1931, founded theoretical computer science by using the integers as a universal programming language. And then he wrote down sentences that talk about themselves and say things such as, I am not provable through a computational theorem-proving procedure. And either that sentence is true, but then it's not provable, so there must be stuff that is true but not provable, or all of mathematics is flawed. And so the self-reference trick I apply to this thing which I call the Gödel machine, which is a machine that has an initial software, and part of that initial software is a proof searcher, and some initial strategy of interacting with an environment, and the goal is to maximize future expected reward as always. But there's an axiomatic description of the hardware of the Gödel machine, which is also part of the initial software. And there's also there's this proof searcher which I mentioned, which is also part of the initial software. And the initial software plus the initial hardware is essentially fully described within the initial software, which is possible. No problem with circularity or something. And then the machine tries to use the proof searcher to find a proof that the execution of a particular program, let's call it Q, will rewrite the original software of the Gödel machine in a way that provably, according to the current proof, leads to more reward, to a better utility of the entire software than the previous one. Now, if you think about that for a while, you will see that this is an optimal self-change, because the proof must have contained already the recursive proof that it is not worth waiting for an even better program Q found even later through this additional proof search by the proof searcher, and that this current self-change has to be executed now to become something that is maybe very different from the original Gödel machine, which maybe doesn't even have a proof searcher anymore. So that, in a certain sense, was an optimal self-improver. We can initialize it by a method which every computer scientist should know, but I found that many computer scientists do not know it yet. There is an asymptotically optimal, fastest way of solving all well-defined computational problems. And this one was developed by Markus Hutter in my lab in 2002. He was a postdoc, and he's another Bavarian genius, just like Sepp Hochreiter is a Bavarian genius. Suppose you have some problems, such as traveling salesman problems. Who knows what is a traveling salesman problem? Okay, good. Almost everybody. So now, the more cities you have in your traveling salesman problem, the harder it gets. Now, this machine, or this meta-algorithm here, what does it do? Given some description of what you want to achieve, it searches for the proofs, again it searches proofs, until it finds a program Q that provably computes the function that you want to solve quickly, f of z, for all elements of the domain, for all traveling salesman problems, for example, within a certain time bound, which depends on Q and on the instance z. And then, while you're doing that, and new proofs are coming in all the time, you spend most of the runtime on the Q, which has currently the best proven time bound. It turns out that this system, this simple method, is as fast in solving your problem as the unknown, fastest program that does that. Save for an additive constant, which does not depend on n, on the size of the cities. Which means, although this additive constant is large, it vanishes as n becomes larger. Which means all large problems are already solved. Almost all problems are already solved because almost all problems are large problems, because there are only very few small problems where the constant overhead still plays a role. Unfortunately, in this universe, almost all problems that we are looking at are so small that the constant overhead does play a role. So that's the only reason why we are still in business and why we are trying to do other things that are not only asymptotically optimal, but also optimal in a practical sense. So one thing that this fastest way of solving problems does not exploit is it does not try to reduce the constant overhead by exploiting solutions to previous problems. So if you first solve that problem and then that problem and then that problem, the programs that solve these previous problems often can be exploited to solve later problems more quickly. And that's what the Optimal Order Problem Solver of 2004 does, which I published in the Machine Learning Journal in 2004. And without going into all the details, just look at this tree here that we have done. And there is a program in the nodes. And here it says while and then bracket, x smaller than y bracket, call fn17, which is some self-defined function that the system itself, the program such as self-defined, which may be a recursive function call of the entire thing. And now you see that these three branches have different width, and the width is proportional to the probability of moving from that thing to that thing in the syntax diagram of this universal programming language. Now this probability in the beginning is uniform for all possibilities. However, you can change it through instructions that are executed by the programs that you are generating themselves. So a prefix of a program like that may change the distributions that you later have. And for example, here, once you're at this point, then it's very, very likely that the next instruction that you're going to execute is this one here. And if you are here, then with a certain small probability, you can also execute this instruction and whatever. Now, to make this optimal in the sense of universal search of Levin, I have to assign runtime in proportion to the probabilities of the total programs, which have loops and recursions. And this simple basic principle makes it, again, asymptotically optimal, but now I can profit from the fact that maybe in previous tasks I have learned programs that solve these problems which change the probability distributions on search trees like this one here during the search of future problems, and this can greatly speed up solution search. For example, without going into the details, let me show how this was applied to Tower of Hanoi, which is a rather complicated problem for artificial systems. Does anybody know what is Towers of Hanoi? If you have n disks in a Tower of Hanoi problem, how many time steps do you need at least to solve the problem? Who knows that? Exponentially many, 2 to the n. So if you have 30 disks, it will take the fastest program for solving that problem 1 billion steps, 2 to the 30. If you ever try to solve the Tower of Hanoi problem as a student, then you will rediscover the double recursive solution here. And that's also the one that the system finds just through search in program space. And it profits from previously learned solutions in a way that allows it to speed up the search by a factor of 1,000. Now, a factor of 1,000 is still O of 1, but it's still very useful in practical applications. These recurrent neural networks are general purpose computers. How can you see that? Well, any program that I can run on this laptop also runs on a recurrent network, because you can implement the central processing unit of this laptop through NAND gates. And through recurrent networks like that, you can easily implement NAND gates, which means you can completely model the CPU of this guy in a recurrent network. At any time step, this guy here is just computing the weighted activations of the units it is connected to at the previous time step. Which means, through these recurrent connections, memories of previous events are circling around in the system. Same for speech. As you are processing speech, you get about one new input vector every 10 milliseconds, and then you get 100 per second, and after 1 second is over, you still have a memory of what happened before in terms of circling activations. The program of the recurrent networks are the connection weights. Each of these connections has a real valued weight, and this weight matrix is the program of the network. You know, before I came here, I thought this is going to be just a small tech talk, but you are actually a large audience by my standards. The other day at the MICAI conference, I gave a talk and there was just a single person in the audience. A young lady. I said, "Young lady, it's very embarrassing, but apparently I'm going to give this talk just to you." And she said, "Okay, but please hurry, I'm the next speaker." These recurrent networks are the deepest of all networks, of all neural networks. And there's a new name for neural networks, which is called deep learning, but it's just a new name for an old hat. If you want to learn more about the history of that field, I think the only comprehensive survey is my own, which has 888 references on 88 pages, and you can easily download it. So there I'm trying to assign credit to all these great pioneers of deep learning. There is also another survey by Lequin and Hinton and Bengio, but they mostly cite each other and they don't even mention the people who invented the methods that they are using all the time. They don't even mention this guy, the pioneer of deep learning, who in 1970 already had deep multi-layer perceptrons with 8 layers. Ivagnenko started in 1965 to train deep neural networks. And the way he did it was he first had a first layer, and then this first layer got inputs from an input layer and just computed the weighted sums or also multiplications. So either sigma pi units, as they are called today, or additive units or combinations thereof. That were his basic features. And then if the problem wasn't solved with that first layer, then he added another layer on top of the first one. And the input to the second layer were the features of the first layer. And so on, like 3 layers, 5 layers, 8 layers, and so on. And then he also had a very smart way of pruning those units that were superfluous by using a separate validation set, which he used to measure the effects of all these feature detectors, and he removed all those that didn't have an important or measurable effect. That was Ivaknenko, and his method was still used in the new millennium. The pioneer of deep learning. The first who introduced deep learning to machine learning was Rainer Dechter in 1986. And then the first group of people who used it for neural networks was Eisenberg and colleagues, who wrote a book in 2000 about deep neural networks, and there they used this expression deep learning. And since then, since 2000, suddenly the usage of the term took off. So that was roughly 2000, and these are the guys who maybe didn't invent deep learning, but they at least invented the terminology. Now, what Ivaknenko, the father of deep learning, didn't do yet was to train the whole system by backpropagation. Who knows what is backpropagation? Who doesn't know what is backpropagation? Okay, so I hardly have to explain that. You have an error function in a deep network, and at the output the network says something that is different from what it should have said, and now there's a way of computing the gradient of the error function with respect to every single weight parameter in this deep network, and the method to go backwards and do that iteratively from the future backwards to the past, that is called backpropagation. And who invented that? No, this was invented in the modern form by this guy here, Seppo Linnainma, in 1970. And he also published Fortran code, so in his master's thesis in 1970. The basic principles were already there in the decade when Ivaknenko did his thing, because the basic principles, from a mathematical point of view, were developed by Bryson in 1961 and Kelly in 1960. A mathematician would say these are pretty much the same methods, but a computer science person would not understand the original papers and would have to look at Linnainma's paper, which was the first who used the efficient modern way of computing error derivatives in sparsely connected graphs such as neural networks. So the method was known but applied to neural networks for the first time in 1982 by Verbas. And then Rumelhart and Hinton and Williams, they used that method at a time when computers were 10,000 times faster than when backpropagation was invented, and they showed that you can learn interesting internal representations in neural networks. That was their contribution. And they did not mention in their paper the inventors of backprop. In 1990, 91 or something, I had my first deep learning project ever, and the goal was to figure out why deep learning doesn't work in these deep networks. Because back then, empirically, it was already clear backpropagation doesn't really work so well if you have many layers, or if you have a recurrent network with lots of time steps in between the important events. And the guy who figured out what exactly is the reason was Sepp Hochreiter, my first student ever here at this university. And in his diploma thesis in 1991, he showed that the main problem is, as you're propagating errors from the future back to the past, from layers at the top of the network down to lower layers, these errors become smaller and smaller over time. They vanish exponentially quickly, or they explode exponentially. Which means you cannot learn much if you have long delays between these relevant events. Sepp Hochreiter. And then a couple of years later, Benjo published the same thing without mentioning Hochreiter. And then the first way of overcoming this in 1991, that was a hierarchy of networks. I call that the neural history compressor, which not only has one recurrent network, but a whole stack of them, and each of them is trained by unsupervised pre-training. Each of them is trying to look at the data and try to encode it more compactly through predictive coding. So it learns to predict the next thing given the previous stuff, and as long as you can predict well, you don't have to store that stuff extra because it's already part of the knowledge of the network. So once you have a rather compact representation of the sequence, you open a next layer with a new recurrent network which tries to even further compress and even further compress the next layer and so on. And finally you have a hierarchy of these recurrent networks, and then you can finally, in many applications at least, rather easily learn by additional supervised training the final goal, which is maybe pattern classification, speech recognition, or something like that. So unsupervised pre-training back then in the 90s could greatly facilitate deep learning in recurrent networks and in general. And we were suddenly able to deal with problems not only with 10 layers or 100 layers, but more than 1,000 layers. So that was the first, in my point of view, as far as I know, the first really deep learning ever. We completely abandoned this unsupervised pre-training by replacing it through a totally supervised system, which is the long short-term memory. Has anybody heard about the long short-term memory recurrent networks? Quite a few. This is what now everybody is using, Google, Microsoft, Apple, all of these guys, for speech recognition, machine translation, all kinds of applications. And the long short-term memory was published in 1995 as a tech report here at this university, 1997 then in neural computation, and it's a very simple trick that is the basis of this network. The very simple trick of the long short-term memory is this unit here, the red unit, which doesn't even have a sigmoid activation function. It just has a linear activation function, actually the identity function. And this means if you assume that this connection here is 1.0, the self connection is 1.0, then as you're propagating errors back through these guys, you always multiply with 1.0. So if you're going around like this, you multiply with 1.0, then you multiply with the derivative of the activation function, you multiply again by 1.0, which means that errors can flow back there not only for 10 steps, 100 steps, no, for 1,000,000 steps without changing. Of course, we know that a linear network is not good enough to solve many different problems that require nonlinearity, so we surround the whole thing through a cloud of nonlinear, multiplicative, and squashing functions and stuff like that, which all learn their own connections through the errors which are being propagated far back in time within these red units. So the red units are the source of all these errors going far back in time, but the other units, they suck out these error signals and use them to adjust their own weights to learn all kinds of interesting behavior. And then you have not only one or two cells like that, but you have millions of them, and with that you can do all kinds of interesting things. For the first time in 2009, we were able to win a pattern recognition competition, namely the connected handwriting recognition competition, and this was done by Alex Graves, who used to be my PhD student in Switzerland, but then became a postdoc during that time here at TU München again. So lots of the stuff which is now super successful is connected to TU München. Keep that in mind. So here we have a handwritten string, T to be willing to hear, and you want to translate that into a short label sequence, T-O blank, B-E blank, W-I-L, and so on, to hear. And the way you do it is you use a method which is called connectionless temporal classification, which we published in 2006 at ICML, which maximizes the probabilities of these label sequences, short label sequences, given these long videos of input streams. And you can compute a gradient of that function. And this thing then does both the segmentation and the alignment and the recognition at the same time by maximizing that. And in 2009, this was able not only to win the French handwriting recognition competition, but also the Farsi handwriting recognition competition and the Arab handwriting recognition competition, although none of us speaks a word of Arabic or Farsi. And our French is also not so good. The same thing, exactly the same thing, can be applied to speech recognition. And that's what all the big companies are now doing. And in 2007, for the first time, we had a system which was better than the traditional speech recognition approach based on hidden Markov models. Who knows hidden Markov models? Okay, good, yeah. So until 2007, almost everybody used hidden Markov models for speech recognition. Now, hidden Markov models are being phased out by LSTM. Today, this combination of LSTM and CTC is used all over the place. For example, Baidu. Well, Baidu used CTC to break the switchboard benchmark record. And here's a whole list of applications where LSTM, long short-term memory, as it is called, is now yielding best results. So why is it called long short-term memory? Because it's a short-term memory in the biological sense. So the biologists, they talk about short-term memory whenever they talk about activations circling around in the brain somehow and representing things that happened a short while ago. And they talk about long-term memory when they talk about weight changes, synapse changes, which last for months or years or whatever. Now, this is called long short-term memory because it's a short-term memory, but it lasts for a long time. So it's a long short-term memory. And it's now used all over the place. Sometimes people ask me, do you have a demo? And I say, do you have a smartphone? Because just a couple of weeks ago, Google Voice had a blog, and there they replaced the old Google Voice thing by LSTM trained by CTC, long short-term memory trained by connectionist classification and temporal classification. And in speech recognition, you are happy if you are 5% better than your previous best system, and 10% is really good. But this was 49% better than the previous best system, and now it's finally implemented. And so if you now speak to your phone, if you have an Android operating system, you can have your demo there. It's an LSTM trained CTC-based system that is doing that now for, I don't know, 1 billion users. The same thing, the same LSTM also works for machine translation from one language into the next. It works for all kinds of for sequence learning in general. So that is what Sutskever and colleagues did, where you give lots of examples of English and lots of examples of French. And then you have an LSTM which reads the English and creates some internal representation of whatever it has read there. And in the beginning it's totally random because all the weights are random. And then you have another LSTM, you can view it as one big LSTM, which unrolls it into a French sentence. And this is a total random thing in the beginning. But then you give it lots of training examples and it learns the structure of English, the syntax of French, and how to go from the meaning of English sentences to the equivalent meaning in French sentences. And systems that use that as a component are now the best machine translation systems in the world. So the same thing, which can do connected handwriting recognition, which can do speech recognition, which can do Google Voice, also can do machine translation. Or image caption generation. I show you that a little bit later because it requires one more little thing. Video to textual descriptions. Or you see a video and you make a text that summarizes what happened. All of that is now becoming a reality. Of course, we are profiting a lot from the fact that every decade computers get faster by a factor of 100 per euro. 100 per euro. Which means in 30 years we have a factor of 1 million. So when we started that stuff, we could do only tiny little toy experiments, but now it's really commercial and all the big companies are using it. Now here's now the thing that I showed you in the very beginning. You can now train a neural network to be a self-referential system. How does that work? Well, you have a couple of output units that can address certain components of the network. For example, weight number 512. And there's an additional extra output unit which can say, change that weight, number 512, from 0.1 to 0.7 or something like that. And in between there are all these recurrent units, and you can run arbitrary weight change algorithms on these internal nodes of the network, which means you now have a recurrent neural network which can run its own weight change algorithm. And now you can train the entire thing to run a good weight change algorithm by creating initial weights that then are responsible for all these additional weight changes during processing of patterns. That dates back to 1993, but then Sepp Hochreiter in 2001 showed, back then we didn't have LSTM yet, but then in 2001 there was LSTM, and a combination of that and LSTM was then the first system that really learned in practical applications a learning algorithm for a small set of functions, all quadratic functions, and this self-learned learning algorithm was faster by a factor of 30 than backprop itself. So backprop, through time, basically was used to learn a learning algorithm which is faster than backprop, running on a recurrent network like that. At least for a certain domain, limited domain. Some problems are so simple that you don't need a recurrent network to solve them. In 2010 we found a way of taking these old methods invented by other people, by people like Lina Inma and Verbers, make them really fast on GPUs and then could outperform all kinds of previous competitors. Twice we kind of led this movement from totally unsupervised systems or unsupervised pre-training based systems to totally supervised systems, like in the 90s from unsupervised pre-training in stacks of recurrent networks to LSTM, and then in the 2000s from something which is called deep belief networks, very similar to this 1992 system, to just fully supervised feed-forward networks which can be accelerated by GPUs in a way that was pioneered by Dan Shirijan from my lab, who is now a senior researcher in my lab, and he made it really fast. So convolutional networks go back to Fukushima 1979, where you always have a network which looks at the first input layer and does convolutions on it, and then downsampling convolution, downsampling convolution. He called it a neocognitron, Fukushima 1979, and then Lequin, 10 years later, propagated errors, applied backpropagation through these networks to get good results. And then Wang had something which is called max pooling, which is used a lot today in 1992. And Shirijan, Dan Shirijan in my lab, and colleagues greatly sped that up such that it became really useful. And then, for example, we could win the Chinese handwriting competition in 2011, although none of us speaks Chinese, and we could even achieve human competitive performance on Chinese, but then also human competitive performance on European numbers, almost twice as good as previous results by others. And then we also in 2011 had these traffic sign recognition contests in Silicon Valley, where the goal was to recognize traffic signs for self-driving cars, and there for the first time a team led by my postdoc Dan Shirijan outperformed all the others and achieved even superhuman performance, which was funny back then because that was a qualifying, and first in the qualifying any team in the world could go to a website and try to improve its standing, and only the top 10 systems would then go to San Jose, where the final competition took place. And until the last day of this qualifying, our team thought we have a comfortable lead, but then right before the deadline, on the day before the deadline, our competitors from New York University, Yann LeCun and his team, submitted another entry which was slightly better. And then Dan and Jonathan and Uli had to work late night to submit yet another entry just a few hours before the deadline, just to re-establish the correct order. But then in 2011 in Sarkozy, there was no close call at all. Our system really was by far the best, 0.56% error. Humans twice as bad. Then third, our colleagues from New York University, promptly hired by Facebook and by Google. And many people are using that now. For example, the AlexNet by Krzyzewski and colleagues. 1 year later was very much like what we published in 2011 at HCI. Of course, it's important for self-driving cars, and that is the pioneer of self-driving cars, Ernst Dickmanns. He's living in this city. And in 1994, he had these fast self-driving cars on the highway already, 20 years ago. 20 years ago, he had cars on the highways about 3 times faster than the Google cars today. He was going up to 180 kilometers per hour. And he didn't use LiDAR and stuff, because that would not have been appropriate, because he had to look far ahead, at least 300 meters, because he was going so fast. So he had active vision cameras in there, with computers 1 million times lower than today's computers, or at least 10,000 times slower than today's computers. And often for 100 kilometers, without any intervention from a safety driver who was responsible for construction areas and stuff like that. Passing other cars automatically, the pioneer of self-driving cars, 1994, 20 years ago. I recommend to the machine learning meetup people to invite this guy. The same thing which helped for the traffic sign recognition also can be used to segment images, and that was the first time that somebody won a segmentation contest, brain scans. In 2012, our team did that. And then very important medical applications, and in 2012 for the first time our team won a competition, or any team won a competition through deep learning, in the medical field, where you have scans of human tissue from breasts. And there the goal is to look at all these cells here and the microscopy images, and you want to find the bad ones, the pre-cancer stage cells, mitosis cells as they are called. Again, there was a competition, and our team with Dan Shirijan was able to win that. And then also next year the MICAI Grand Challenge, which addressed the same topic, which is so important in the medical field. And the MICAI, by the way, the MICAI is taking place right now in Munich. And right now, as we speak, there is another talk by a Nobel Prize winner, by Gert Binning, the inventor of or co-inventor of the tunnel electron microscope. And he will be so disappointed to see that nobody shows up because you are all here. And then image caption generation. That is again Google, a combination of CNNs, which we had before, convolutional networks, and LSTM. So you see an image like this one here, and it's piped into a CNN front end and creates an internal representation, and then there's an LSTM, a long short-term memory recurrent network, which is supposed to translate that internal representation into text which describes the image content. For example, here it says, what does it say? A herd of elephants walking across a dry grass field. And you look at the image and it's true. Or here, a group of young people playing a game of Frisbee, and the only Frisbee thing is these few pixels over here. So, although it's not always perfect, it's pretty good. And remember, every decade we are getting a factor of 100, and at the moment this is all scaling linearly. Here's a bad one. A yellow school bus parked in a parking lot. But it's getting better all the time through training. What you really want to do is reinforcement learning. And in reinforcement learning, there's no teacher, like in the supervised applications that we had there, which tells you what to do at which point in time. Instead, the system itself has to come up with a sequence of actions that lead to desired results, like here, not crashing. And the fitness function that this system is maximizing is just the time or the distance traveled in a video game simulation, a car simulation like that, on the racetrack without crashing. No unsupervised pre-training, no teacher who tells the system at time step 55 you have to accelerate that way and to brake that hard and to go left or right or whatever. It has to figure out all of that by itself. And through reinforcement learning it learns that. So there are even now recurrent neural networks that can reinforcement learn from raw vision input, because what these networks see is raw vision input like that streaming into the recurrent network with almost 10,000 pixels 25 times a second. And it has to learn the vision pre-processing, the translation from this vision into actions, steering, braking, and so on. And this can be done through a method called compressed network search, which now I won't have time to tell you the details of. There won't be another NN Winter, simply because the machines that we will have in the future, the hardware on which we are learning programs, will look more and more like recurrent neural networks. Because that's the nature of the computing machinery you need for this type of universe, where you have light speed constraints, where you have energy constraints, where you have 3 dimensions, where you can place your processors. So it will be, all future hardware will be a collection of densely spaced multiple processors connected through many short wires and few long ones. Essentially recurrent networks. What we will see a lot is what we have started about 25 years ago, one network which is controlling a robot or something, and another network which is modeling the consequences of that. So a recurrent network which is predicting what's going to happen if I do that and that, and a controller which is really executing the actions, and the controller can profit from the predictions of the model. So as the model is learning better how the world works, the controller can exploit the predictions of the models to come up with better action sequences, to plan better action sequences, to learn better action sequences. Reinforcement learning again. This is also 25-year-old stuff. My first paper on that was really 1990, but now it's coming back a lot with a vengeance, because computers are now fast enough to make that a reality. Back then also we had the first attentive vision systems, which are based on this principle that I just mentioned, where you learn then a sequence of saccades on an image such that you attend to the important stuff in the image, and you make sure that your limited computational resources are spent on the few important things as opposed to on everything, where you have a sequence of saccades similar to the ones that humans execute all the time as they are observing visual scenes. Also, old stuff, 1991, but now coming back with a vengeance. I won't have time to talk about all kinds of things here. Let me just mention what we will see next. I think what we will see next is something like a little monkey, like a little capuchin monkey, which can do the things that current machines cannot do yet, namely, with a recurrent world model, predict all these consequences of their actions, and with a recurrent action selector come up with good actions, but in a way that is different from what the traditional old systems of 25 years ago did, but in a way that that learns to focus on the important stuff in time, where you have a system that learns sub-goals, relevant sub-goals. Instead of simulating futures millisecond by millisecond, they will learn to jump ahead, and for example the little capuchin monkey sees a tree and up there's the fruit, and he quickly comes up with a decomposition of his options in the future by saying, okay, now first I want to use a subprogram which is running, which I use to get to the base of the tree. There I invoke another subprogram for climbing up the tree, which I already know, have learned in previous tasks and previous parts of my life, and there I invoke another subprogram which is grab this fruit and lead it to my mouth, and so on. And at the moment we don't have good systems yet that really can do that, can do this hierarchical or abstract planning, but I think we are almost there, and I guess a couple of years will be needed to have a little monkey which then quickly learns new things on top of the old things that it already has learned. If you ever saw one of these little capuchin monkeys in the zoo, for example, you will see they can do almost everything that you can do. Selectively attend, take into account the social context. Is there maybe another capuchin monkey which is watching me, which also has discovered that fruit, and do I have to act as if there's nothing up there? All these hierarchical abstract reasoning processes are already there in these little monkeys. We just can do more of those because we have 1 liter of brain and they only have a few cubic centimeters. But the basic principles are there. Once we have that, the step to human level intelligence, I think, will not be so huge. It took billions of years to evolve a capuchin monkey, but just a few millions of years to evolve human level intelligence on top of that. We have a company which is trying to make that a reality. So this basically concludes my little presentation today. I wish to thank the organizers for organizing all of this and for the check which I'm going to spend on my kids. I wish to thank my mom and my dad, without whom all of this would not have been possible. And I wish to thank my kids, without whom all of this would not have been necessary. And thank you for your attention.